Okay, so this is where we left off last time. We started on the acid-base stuff. This is kind of mostly review, hopefully, for most of you. So pKa values and acid-base strengths. So what is a pKa value? What is that? What does that capital K mean? So every single part of that, P, lowercase p, capital K, and the A here, all tells you something, doesn't it? Okay, so the capital K means what? Equilibrium constant. Yes. So it's an equilibrium constant. It tells you which side is favored. Specifically, a capital K is actually grouped up smaller k's. Remember the rate constants we used to talk about back in Gen Chem? Okay, so those rate constants were lowercase k's. If you group them up so they become a value that doesn't change depending on how much you have, right? An intensive value, like a density would be, then these become a capital K, which is telling you equilibrium constant. Now, specifically, this one is for an acid reaction, isn't it? See that little A there? That's what that subscript A means. Okay? What does a P mean? Like if I was to say pH, POH, PK. Negative log, you got it. So it's a negative log of that value. Okay? And you do that because when you're talking about binding constants, when you're talking about, even for like diseases, for example, COVID, when they were talking about the binding constant for an antigen, these values, typically like a 10, 20, 30%, is pretty much meaningless. Okay? That's why a lot of the medical professionals were like the boost, that second booster, remember that? After Omicron, they were like, this is fucking useless. Why would you get this? It's the health outcomes for getting it are worse than the improvements for getting it. Like, this makes no sense. And it became mandatory, in fact, which was pretty messed up. But the reason they were saying that, despite it being a 30% improvement in binding, is because bindings are a logarithmic scale. Okay? So a noticeable difference in binding is a 10 times difference in binding, right? That'd be a what percentage increase? 10,000% increase. Like, that's okay, you have some improvement. Okay? When you are talking about a very large scale increases, again, they're going to be like a pH difference of 3 means it's a 1,000 times difference, right? In your H plus concentration. Okay? And same thing with these. These are, again, going to be a logarithmic scale of which side is favored. Does anybody remember, is it large values or small values that tell you the products are favored for a Ka? Yeah, so the equilibrium constants were always the products over the reactants, right? Okay. So large values told you products were favored. Small values told you what? Reactants were favored, right? If the value is less than 1, then reactants are typically favored. Okay. Now keep in mind that these are actually 2 powers here, so they can have powers. So it's a little bit more complicated. We'd have to go through a whole review of what was essentially half of Gen Chem 2, right? If we wanted to go through all that again. Okay. So in this case, because we're doing a negative log of, so if we're a larger value of pKa, what does that mean? Larger value of pKa is going to be a smaller K number, right? Okay. So If the acid is stronger, then that's going to mean you're going to make more products. The Ka value would go up, right? Okay, and it would be a larger value, right? But because we're looking at a negative log of value, what does that do when you have a larger value? Anybody want to try it? Got a calculator? Okay. Type in negative log of 1. What do we get? 0. Negative log of 1 is 0. Negative log of 10. Negative 1. Negative log of 10,000. Negative 4. And so what direction is this going? Yeah, negative. Yeah. Yeah, we're going to be going downwards, right? Yeah. Okay. And so, again, if your reactant side is favored, it's going to go the opposite direction, right? Okay, your Kas will get smaller valued. Your pKas, on the other hand, are going to become larger positive value numbers, right? Okay. Okay, so again, this is a base reacting with an acid. This is the typical acid-base reaction. When we do acid-base reactions, the definition always defines it as being one proton being donated, right? And so you always write every acid-base reaction as a singular proton being donated, okay? This actually has a lot of mathematical applications, but for this course, we don't really do that much of that, okay? So this is the conjugate acid. It's what the base is always going to go to. Notice that we always end up forming an acid-base pair when we're talking about bronze-slurry acids like this. And then we're going to have here the acid, which goes to its conjugate base. Okay, is everybody good with that so far? Fantastic. Okay, so again, a lower pK is going to represent a value that represents a stronger acid. And again, this is because if you want to get rid of that P in the pKa and just go to Ka, it would be a 10 to the negative power pKa. Okay? Meaning that large pKa values have very small numbers, right? Okay. Each difference in one pKa, again, is going to be a 10 times difference in acid strength. So if we have a pKa value that's 1 versus a pKa value that's 4, what sort of difference in strength are we looking at? Yeah, 10 to the third or 1,000, right? Okay. So it's a very, very large difference in strength when you're talking about pKa's, right? Or another way of saying that is a 20% difference in terms of acid strength isn't a lot, is it? It's not a particularly meaningful number. Okay. Table 6.1 actually lists the pKa values for several common acids. There's even more values in Appendix A. If you ever want to get pKa values in this book, you'd go back to Appendix A. Does everybody know how to get to the appendices and such? Okay. Okay. Again, so in your general chemistry, okay, what was the pH range we were typically talking about? Come on. What's the low end? 0 usually, yeah, you guys ended up only going to 0 usually. Technically, it should have been -1, but most general chemistry books sort of lightfoot around that and try not to deal with it. What was the high value for that? 14, exactly. 14 is close enough. It should have been like a 14.3 something or somewhere in there. Okay? It kind of depends on your definitions and temperatures. The reason why I'm saying that, and I'm like, the book was a little wonky, is because those values are based on water systems at standard temperature pressure. Okay? And so that's why you're always limited to like a -1, 0-ish to a 14. Is because once you get to those values, you're reacting with water, and everything else gets reacted away. And you're just left with the water system. Okay? Are we always doing everything in water? No. So guess what happens to our pH ranges? Yeah, we can have like a negative 20 pH. We could have a positive 30 pH. Okay? We can do all sorts of crazy crap that you would never imagine back in general chemistry, right? And that's because we're not going to be working in water systems. Okay? We're going to be working in a lot of organic solvents. And so our solvent, well, it does limit the pH range we can work in. Not as much as water systems did. Okay? And so we can get some pretty crazy stuff. This is where things like superacids, if you ever heard of that, come into effect. Okay? You'll notice that I'm already talking right here. They could range from 10 to the negative 50, which is the pKa 50 ethane, to 10 to the 13, which is trifluoromethane sulfonic acid, which is pKa of negative 13. So right off the bat in this organic chemistry textbook, that's just the like basic intro to organic chemistry. We're already ranging that, right? And that's a pretty good range to kind of encompass in your head. So keep that in mind. We're not limited to 0 to 14 by any means. Okay? These are actually mostly our limits in organic chemistry. You'd have to really contrive a situation to get past that. This actually means that like trifluoromethane sulfonic acid is 10 to the 63rd times stronger acid than ethane would be. Okay? Both of them are acids in the organic sense. Both of them can donate protons. But that's the sort of differences we can look at, okay? All right. So let's predict the outcome of a proton transfer. So what are you always going to trend towards? Do you trend towards the stronger acid bases or the weaker acid bases? Weaker. And that's the definition actually tells you that, doesn't it? What is a strong acid? It's something that loses its proton easily, right? What is a weaker acid? It's something that does not lose its proton as easily, right? Yeah. And so definitions can actually help you a lot in this. If you understand your definitions well, you can predict where problems will turn out. Okay. So again, here we have a stronger acid. It is going to a weaker acid here. And that's why this side is favored, right? Right here we have a weaker acid. We're trying to go to a stronger acid, and so which side is favored? Yeah, the reactants. We're going to stay as reactants mostly, right? Does that mean we're not going to make any product? No, there's going to be a little bit on that side, right? But very, very little. There's a pretty dang big difference here, right? Okay. If you haven't already joined up, please join up the classroom. And by the way, in case I haven't mentioned this, did you guys see the number there? So if you're ever something not camera or you're having trouble with QR code, or you just don't feel like doing QR codes, you can actually go to that slido.com and enter that number. That's the number for this. Yeah. Okay. So let's predict which side is favored and to what extent that side would be favored. Now, you actually kind of know a lot of these from your previous biology and your previous general chemistry, okay? So let's see how well you remembered what things are more acidic or basic, okay? Okay, so here we have an alcohol, right? Or carboxylic acid, excuse me. And it is losing a proton, and it is giving that proton to an amine, isn't it? Okay. And so is it favored to be this side, products, or this side, reactants? Don't answer. I'll put a quiz up in a bit. Just have it ready in your head, okay? And ready to put down. Okay, we all ready? Fantastic. Okay, I think everybody probably has it, right? Okay, very good. Okay. Get ready to answer. Which side is favored? Products or reactants? Okay. Okay, I'm going to go on. Go ahead. Okay. All right, we'll go on. Oh, wow, we had a large diversion of opinion. Okay. And so, luckily, the majority did answer products. Fair enough. Good deal. This is a pretty significant difference, in fact, in this case. So here we have something that's a carboxylic acid, and this is something that's fairly well known as a base. Okay? So this right here is going to favor going to the products quite a bit. Right? Anybody have any questions? No?
Okay. How would it look slightly?
Huh?
How would it be slightly? Like instead of the greatly, how would it be slightly?
Oh, slightly would be something that's like a carboxylic acid, something that's not basic.
Right.
Yeah. So for example, we could take something that would be like a H2SO4, and there'd just be a small difference in the acidity between those. Okay? It could still act as a base, but there's not a lot of difference between these, acidity and basicity. Happens a lot in like the triprotics. For example, your DNA has those phosphate backbones, which are the very analogous to like phosphoric acid having lost a lot of its protons. Those can act very subtly with very small differences. Okay. Amino acids are another one that happens a lot, where you have actually very subtle differences that can cause protonation, deprotonations. But honestly speaking, I would take either for this case. Yeah, it's not a huge difference like a strong acid would be. Okay, but it's fairly strong. So a stronger base is going to be one that has a weaker conjugate acid. The strength of a base is the weakness of its conjugate acid. Okay. Alternatively, the weaker base is going to be one that has a stronger conjugate acid. You can always think of it as a duality. Is that making sense? Okay. All right. So, which base is stronger, H minus or HC triple bond C minus? Well, the conjugate acid of H minus is H2. It has a pK of 35. The conjugate base here is this one right here, which has a pK of 25. So, again, if we want to figure out which one of these is going to be a stronger base, then we really want to look at its conjugate acid, right? Because the conjugate acids are something that you can actually have populations of. Okay? These are all both extremely reactive. You can't, like, buy a bottle of either of those. Okay? You'd have to generate those in situ in your solution. All right, so H minus is actually a stronger base, and that's because the H2 here is a weaker conjugate acid. You can see that from the 35 here. This is a stronger conjugate acid, meaning that it's going to be a weaker base. It's not as likely to take on a proton. Okay? Another way of thinking about that is it will fall back apart easier. Okay? All right, so the leveling effect. When we want to carry out a particular reaction, we typically do not want the solvent to react with the species we add. That would be counterintuitive. Like, remember, what is the species you have the most of in any given solution? The solvent, by definition. Yeah. So every solution is composed of solutes and solvent, right? And by definition, the solvent is the one you have the most of because everything else is dissolved in it. It doesn't have to be water. In fact, many times in organic chemistry, it will not be water. Okay, but yeah, in general chemistry, there's always water because that's general chemistry. So, when your reactant is going to be too strong of an acid or base, it's going to react with the solvent. An undesired proton transfer reaction will occur, and you will end up acidifying your or causing your solvent to go basic or acidic. Okay, and you'll end up with the acidic or basic form of your solvent, rather than any form of reactant at all that you were planning on using. So in this case, your reactant doesn't remain intact. It can't undergo the desired reaction if you don't have any reactant that remains intact, right? So an undesired proton reaction is going to be a result of what's called the leveling effect. This has a fancy name to it because it's fairly common and something that you really do have to watch out for. So the strongest acid that can exist in a solution to any appreciable concentration is the protonated solvent. Everything else can't exist in any appreciable concentrations. Strongest base that can exist in solvent is going to be the deprotonated solvent. With the solutes, you can get around this to some degree because they are not such huge concentrations, they are sure to react. Okay? But the solvent is always a large concentration, larger than any other species. So everything always reacts with solvent. Okay? By the way, that was actually why acid-base reactions in water typically do their acid-base reactions through water. If you're ever paying attention to your equilibriums, they always went through the KW, right? Whenever you were doing acid-base reactions. That was why. Okay? Because you were running into the leveling effect quite a bit. That's why the strong acids don't have any designations after that. And just say infinitely deprotonated, right? That was actually the leveling effect. Okay. So in water, no acid stronger than H3O plus exists. No base stronger than OH minus exists. That's why the pH scale is that 0 to 14 or negative 1 to 14, depending on the temperatures. Again, that's because the acid, for example, HCl, strong acid, is a stronger acid than the H3O plus, and so all of the HCl automatically reacts with the H2O to form H3O plus. We won't have any HCl remaining as soon as we put that into water solutions. The base is stronger here. We have a stronger base than water, and so again, if you put that base in water, what's going to happen? It will immediately react and give you the products here, and you're going to have no appreciable amount of the base you put in water, right? Okay, so if you're trying to use this for a reaction, will you have that? No. Nope. That'll be all gone. You'll have this. That's the base you'll have. Okay? Okay. Okay, so choosing a solvent. If we want to carry out a reaction involving things like an HCl or a dimethylamide as a reactant, then the water is going to be a poor choice for solvent because both of these species are going to have the undesired transfer of the water. We can avoid using unsuitable solvents to avoid proton transfer reactions. We can look at the solvent if it's suitable to a particular reaction. If it is a stronger acid than the solvent's conjugate acid, and therefore we have a pKa that's lower, it would be a suitable solvent. If the stronger base than the solvent's conjugate base, so if your conjugate acid, R, has a higher pKa than the solvent, then it would be suitable. Okay? Essentially, you just need it to be higher. By the way, if they're close to each other, you will actually limit your amount of species that can react. Okay? But eventually it will push the equilibriums through, and you will get your reactions. It just might slow it a little. Okay. Any questions? Oh, a bunch of people answered in the... okay. That's fair. All right. So here we have a strong base. Let's verify that your diethyl ether is a suitable solvent for our strong base here, according to the leveling effect. So what you want to do is you want to go back into a table, right? And you'd want to look at these pKa's. So which of these has a higher pKa? And then remember that you are looking to use this as a base, right? So you need that one to be a better base than this. Okay. Okay, everybody have an idea in their head? Okay. Are we ready? Everybody get a chance to look at the table? Or look them up on Google? Either way. I'll be honest. Google searching them is usually faster than the table. And if you want to be even faster, then have Wolfram Alpha available. And it usually does a pretty good job. All right. Ready? Set. Go. Huh? Oh. Sorry, we passed through that. Yep. Oh, nobody wanted me to leave them alone. Okay. Okay. And so, yeah, that's actually correct. Okay, so if we look them up here, we can see that this right here has a pKa 38. That's lower than the pKa right there. Okay. And so this right here is a better base, as it were, than this. And so this would be the possible reaction. Now, if we look again, this is the stronger acid here. Okay? This one's a weaker acid. Is that making sense? Okay. Okay, fantastic. All right, so, excuse me. One of the ways you can help yourself figure this out, by the way, is, again, what does an acid have to do? It has to lose a proton, right? So you can look at the groups that would be more likely to lose protons. Okay. All right, so equilibrium, this is going to be the rate of the reaction in the forward direction equaling the rate of the reaction in the reverse direction. So they're going at the same rates both ways, and so they stay consistent. Does that mean that both sides has the same amount? No. The two sides don't have to be equal amounts, do they? They just have to have an equal rate of exchange. Okay? All right, so in this right here, we can have some of the ethanoic acid that would exist in solution. This is actually a weak acid, and so it will actually favor this side. We'll have mostly intact ethanoic acid. Some of the ethanoic acid will fall apart in water and form the ethanate ion. Okay? And this is because this H3O plus is actually a little bit better acid than the ethanoic acid, but there's not such a huge difference that goes almost all the way to one direction. Okay? All right, so everybody remember Le Chatelier's principle? Yeah? No? Okay. It's where you can tip equilibriums. So if a reaction at equilibrium experiences a change in reaction conditions, typically these would be things like concentrations, temperatures, pressures, volumes, then the equilibrium will shift to counteract that change. Specifically, things like reaction can shift in the forward direction by the addition of reactants or the removal of products. So if you were to react away this right here and it goes away, this would keep going and populating that, wouldn't it? And so you would get a shift towards the right direction, okay, or the products. You can do the reaction can shift in the reverse direction, of course, if you add products or you remove reactants. And so that would cause a shift towards the reactants. For example, if we added an acid that creates more H3O+, we would shift this reaction the reverse direction, wouldn't we? Okay. So pH, this is going to be the concentration of H3O+, reported as a negative log. So when we talk about pH, this is going to be negative log of the H+ concentration. In water, that H+ concentration will be in the form of H3O+. Okay? Those are synonymous when you're in water. Everybody okay with that? These memories starting to come back? Okay. So let's look at that proton transfer in water again. This would be a acid, HA, that's the generic form of an acid, literally an H attached to an anion. So HA. This is reacting with water. It's going to leave the conjugate base, A-, and we'll get H3O+. This will form an equilibrium. This HA specifically stands for weak acid. So lowering the pH of the solution is going to shift the equilibrium towards the HA. If we raise the pH of the solution, it's going to shift the equilibrium towards the A-. Everybody okay with that? Okay, so let's talk about the ionization states. The dominant ionization state, is going to depend on your solution's pH. So the HA here is going to be the dominant form when the pH of the solution is lower than the pKa of the H-, the HA here. And what that's telling you is that when the pH is lower, something else is donating protons to that and is going to keep doing this reaction in that direction. Okay? When you have a higher pH, what's going to happen is that OH-, that higher pH, what's causing that higher pH, is going to continuously remove H3O+ from this, and that's going to push it towards the products. Everybody okay with that so far? Okay. The HA and A- is going to be in equal amounts when the pH of the solution equals the pKa of HA. Anybody remember your Henderson-Hasselbalch formulas? No? Okay. Anyways, there was a special place where you could go pH equals pKa. Yeah. And that's actually what we're talking about here. And that's because the HA is going to equal the A-, right? Half and half at pH equals pKa. All right, so reaction's tendency to form products is going to be the equilibrium constant. This is KEQ. Notice that Ka was just a special form of this. That was specifically for acids, right? What would the Kb be for? Bases. You got it. Okay, and so right here we see the KEQ. This is the generalized form. You can figure out KEQs for anything. It would be the products over reactants. Everybody remember that well enough, or do we need to chant that? Products over reactants. Seriously, it helps if you say it a few times externally. This is always to the power of their coefficients. Can everybody see it okay? Okay, and remember the KEQ only exists and is only valid when you are at equilibrium. Okay, it will tell you the concentrations you'll have at equilibrium, right? Or the state of your reaction at equilibrium. So, again, here is a KEQ. This one is actually for an acid-base reaction right here. And again, that would be called a Ka when we have an acid reacting with a base. Okay, and so we see the products here, reactants here. Why are they all coefficients 1? For an acid and base, you always define the reaction as a transfer of a single proton. And so all the coefficients always have to be 1. Yeah, That's actually a fun trick we play. Okay, so very large KQ values, 10 to the 10th is going to heavily favor the products because that's the one on top, right? If we have very small values, 10 to the negative 10th, that's going to heavily favor reactants because that means we have a very large denominator. If we have something that's close to 1, then that's going to favor significant concentrations of both reactants and products, i.e. another way of saying that is both sides are pretty close to the same thing, right? Notice that these are not actually directly comparable, okay? So if you try to compare KQs for several different reactions, you can run into a lot of trouble, right? And that's because of the powers. For KAs and KBs, they're very comparable because the powers are 1, okay? For KEQs, you got to be very careful. So the Ka values, this is going to be the acidity constant. That's where the A comes from acidity. Two acids compared, one with the larger Ka values, the stronger acid, because it makes more H plus in solution. Again, this is the pKa. It's the negative log of the Ka. Anybody remember how you want to do a negative log, by the way? Uh-huh. What if we want the Ka? Yeah. So we would go 10 to the negative power of the pKa, right? And that would equal the Ka. That's how you can undo one of those. Okay. So you may remember the Henderson-Hasselbalch equation. It's going to be a common general chemistry equation. It's used for the dealing with buffers. Anybody going on to like biochemistry or having any idea of going on to like med school, this is going to be a pretty popular question. Okay, a little bit less popular now than it was, but still a pretty popular question. So it is the negative log of the Ka, which is the pKa, right? Equals pH minus the log of the A minus over HA. Okay. This right here is the Henderson-Hasselbalch equation. By the way, if these two numbers are equal, A minus and HA, i.e. 50% population in each, right? That would be a 1 inside there, wouldn't it? Anybody remember what the log of 1 is? 0. And so that would actually leave you pK equals pH, which is what I was talking about before, right? Okay. Anybody remember what a buffer solution is? Okay. That's where you have a weak acid or weak base that's partially dissociated, and so both sides of the equilibrium can push back against change when you add any more acid and base in it, right? i.e. it resists pH change when you add an acid or base in it. Okay. By the way, this is the rearrangement in case you're curious. Anybody have any questions about Henderson-Hasselbalch? Okay. So this is going to be the proton transfer equilibrium right here again. And again, this is where the KEQ equals the 10 to the change in the pKa. Where the change in the pKa equals the pKa times the concentration of the HB minus the pKa of the concentration of HA. When HA is the stronger acid, the pKa HA is going to be lower than the pKa here, and so your pKa difference is going to be a positive value. This is how you tell which is going to be stronger and how much it's going to be stronger. This also works nicely to feed in whenever you have an energy equation. So if you want to go ahead and figure out the energy differences between the two, you'll end up having to calculate this. Okay. Anyways, the HBA is a stronger acid if the pKa is higher than the pKa for the HA is higher than HB, i.e. the pK difference is negative value. So let's talk about why things are the way they are. So if we favor products, what does that mean about that reaction in terms of energy? Ooh, I wonder. Yeah, so we have an interesting thing going on. Does anybody remember what Gibbs free energy is for an equilibrium? Zero. Yeah. So equilibrium means no side is going spontaneously, is it? Or another way of saying that is both sides are equally spontaneous. Okay? And so the delta G at equilibrium has to be zero. Now, if we have not reached equilibrium yet, what side is favored if the delta G is negative? Negative delta G means the reaction is spontaneous going towards products. What does a positive delta G mean then? Spontaneous going backwards, right? Towards reactants. Very good. So if it has a value less than 0, by the way, that's again going to be referred to as exergonic. Notice that's not exothermic. Okay? So exergonic, not exothermic. What was exothermic, by the way? Delta H, right? Yeah, that was for delta H, releasing energy. If the delta G reaction is greater than 0, then that is endergonic. And if it is 0, then that means what? It's at equilibrium. Yeah. We have no overall energy changes. Okay, and again, if it's greater than 0, that means the reaction, or i.e. the system, absorbs energy. If it's less than 0, that means that the reaction or system is releasing energy in the surroundings, right? Now, keep in mind that when we're talking about Gibbs free energy, that could be entropy that we're talking about, but that can also be enthalpy, right? Okay, which are two very different ideas of heat and energy, okay? All right. So, this is the free energy diagrams for this, and this is in many ways the easier way to understand these things. So here we have reactants. They're undergoing a reaction. They're going to go through the transition state. See that? Okay. And this is the amount of energy you have to overcome, isn't it? This is denoted by delta G naught with a double plus sign. See that? That's the high energy state, or another way of saying that's the barrier you have to overcome, or another way of saying that's the transition state, right? Okay. Once we overcome this transition state energy, we're going to go down to products, and that's going to be the difference here is going to be the amount of energy that would be released by that reaction. Okay? Anybody have any questions so far? All right. So here we have, again, another energy barrier where we have to overcome right there. Once we overcome that barrier, we would go down to products, but does this one release energy to its surroundings? No, this one would take up energy from the surroundings, wouldn't it? Yeah. So this one we would have to continuously putting in energy to drive it forwards. This one, on the other hand, would most likely drive itself forwards. Okay? Okay. Okay, so this is how these two things are actually related to each other. So this is the delta G naught of the reaction. Anybody remember what naught means here? Under standard conditions, right? Okay. Does anybody know what a naught prime would mean? A naught prime, where you put a prime behind the naught. Modified standard conditions. Most likely physiological conditions. Yeah. So they make a whole series of values that are essentially the physiological, what it'd be like in the human body sort of stuff. And then they use those. Yeah. But you can do prime. You can keep going, and you can get a whole series of modified conditions. Okay. So again, the delta G naught reaction equals negative RT. Yes, that is the R from the gas law, but this is the energy one. Okay? Be very careful if you're putting this in. It's the one with the energy, i.e. joules in it. This is T, temperature. These need to match units, by the way. Natural log, and then KEQ. Everybody okay with that formula? Fantastic. Okay, so again, we can actually break this down into the delta G of the reaction for the delta H minus the temperature times the delta S. And so delta H is what again? Enthalpy, right? Which is heat over constant pressure, isn't it? Delta S here is the entropy. What was the entropy again? Not quite. Randomness is what most people say. Yeah, it's a measure of randomness. Is an okay analogy. A better analogy is it is a measure of the number of possible states. Okay? The less possible states you have, the lower the entropy. Okay, so enthalpy. If we have a delta H that's greater than 0, then the reaction is going to absorb energy, and that's called endothermic. Notice that this would make a delta G that's also positive, wouldn't it? If we have delta H that's less than 0, then the reaction is going to release energy. This is called the exothermic. Note that breaking a bond would require energy. This would be endothermic. You can actually test and understand this because breaking anything always requires energy, doesn't it? You ever notice that? When you break your pencil, what happens? Does it just do it by its own? Or does it require energy to do it? Requires energy. Yep. Exothermic, forming bonds, is going to release heat. It's going to be exothermic. You can think of this analogous to two magnets coming together, right? When two magnets snap together, you hear a snap sound, right? And that's because they're actually releasing energy. Entropy, again, that's the standard entropy difference, is going to be the delta S naught reaction. So a reaction in which the number of separate species increases is going to have a delta S naught reaction that's greater than 0. A reaction where our ring breaks open is going to have one that's greater than 0 as well. And these are both because we would have more possible states that our products can be in, right? Okay. By the way, most of the things that you've probably done in life have not really talked about the delta S as much. Usually the reactions boil down to your delta H's for most of the stuff you've done. However, in your body, actually, there's quite a few reactions and processes that are delta S dependent. Okay? Like a lot of your channel uptakes actually are delta S dependent, which is kind of interesting. All right, so functional groups and acidity. You notice that we've had these functional groups we've been talking about before. One of the reasons they are functional groups, i.e. do functions, is because many of them have acidities that are more significant than the CHs. Okay. All right, so these are some different functional groups and their acidity. Here we can actually see some alcohols. And notice that those would not typically be called acids, would they? If you were a general chemistry student, would you call those acids? No, they're greater than 14, aren't they? But in organic chemistry, because we are oftentimes not in water, these actually are pretty decent acids. Okay? They can very much act as acids. Right here we have the carboxylic acids. These are more typical acids that you've seen before, right? Which is why they're called carboxylic acids. Because they would lose protons in water. Okay. So if we use table 6.1, let's estimate the pK values for indicated CH protons in cyclohexanone. What would these pKa values be? So does it make sense to try to tabulate every possible CH that you could find? No, it's just impossible, right? There's no way we could do that. And so what you're oftentimes going to have to do is find something that is analogous to what you're looking at, right? Something that has a similar set of functional groups. And then use those numbers to predict it, okay? And this is how most of the assumptions are made in science, if your assumption is worth a dang at all. Okay? Note that this is actually becoming sort of a rare thing these days. That's why you've been hearing about the reproducibility crisis. People are making a lot of unqualified assumptions lately. But, yeah. I'll at least teach you how to do it right, I guess. Okay. Everybody ready? You have a general idea? Okay, so when I'm on this screen, if you're not ready to answer, go, wait. Okay, hold up. Okay. Anybody still not ready to answer? Everybody's ready? Okay, ready, set, go. Okay. And, yep, you got it. Okay. Okay. And so, yeah, you got first. Yeah, some of these, apparently, I accidentally got the victory table enabled on there of who got it first. Okay, so why is A more acidic than B, by the way? You got it. That oxygen's going to pull electron density from it, right? And that's going to make it so it's a lot more stable when it's innately charged, isn't it? Okay. Got it. Okay, and one of the ways you could go, you could really just look up any ketone, and you'd be pretty close. Okay? And that A is a ketone, really, right? It's the next one over from a ketone. The B, on the other hand, doesn't really have any functional groups that are very close to it. And so really any chain of carbons would do. Okay? Now, how do things drop off, by the way? Like if it's the second position over, so like this position here, that's going to have a lot of effect from this, right? Not as much as being attached, but it's going to have some significant effect, right? How about the next position? No, that's going to have very little effect. It'll have a little, but very, very little, okay? And then the next one is going to have none, essentially. Mm-hmm.
What happens if there's two carbons between the bond oxygen?
Yep, that's exactly. So if there's one, do you mean this one here and this one?
To the right.
Oh, to the right?
Yes.
So like that one?
Which one would you choose to be more acidic?
These would be equivalent. Okay. And these ones would also be equivalent. This one, though, would have no real effect from that at all. But if you were choosing this versus this one, these would have a bit more acidity. Just a little. But a little. Okay. And you can kind of think of it like the if somebody's like throwing stuff, the first person in the line gets it, right? The second person in the line gets a little. And then the third person in the line, basically at that point, you're going to get almost nothing, right? Yeah. Okay, so there are trends that are going to dictate the strength of an acid. Proton is going to be dramatically more acidic when it's attached to a positively charged atom than when the atom is uncharged. The pKa of the H3O plus is going to be 0, whereas H2O is going to be 14. The pK of H4N plus is going to be 9.4, whereas H3N is going to be 36. And so again, as we make something more positive, it's going to have a significantly more acidic. It's going to be significantly lower pKa, right? Okay. Again, why is that? So by donating an H+, what do we always end up doing? Leaving a negative pair of electrons, right? So the more positive you are, when you become a negative pair of electrons difference, you end up being neutral, right? Okay. And so that helps counterbalance that. Makes it more stable. Okay. So let's look at these two sides here. Which side is going to be favored? The reactants. This is actually autoionization of water, isn't it? Yeah. And this doesn't happen a lot, does it? Yeah. There's like a 10 to the negative 7 concentration of these at room temperature. Yeah. So this is heavily favored, right? And again, you can predict that because the other side has a negative and positive charge, doesn't it? Okay. They're a lot less stable. Okay, let's keep track of some charges. Now, when we do these reactions with acids and bases, we need to be very careful of tracking the charge differences. If you lose an H+, what is that going to do to the thing that lost the H+? Always going to end up with a negative charge and a pair of electrons, right? It's always going to end up with a -1 to whatever its charge was. And it's going to have a spot where it had electrons that used to be consumed by the H+, right? Okay. And so this is actually what we're always going to see, something along these lines. Is everybody okay with that so far? Okay. One of the most common places for students to mess up and have difficulties with this, by the way. Okay. Right here, on the other hand, the thing that gains the proton, what is it gaining? An H and a plus, right? And so the thing that gains the proton is always going to go +1 to the charge, and it's going to gain an H, right? Note that it will also lose a lone pair of electrons being exposed. Okay? Those electrons that were in a lone pair before are going to end up bonded into a bond, right? With that H+. That's called a coordinate bond, by the way. Coordinate covalent bond. Interesting little factoid. Somebody just showed the existence of carbon-hydrogen bonds with one electron. So that was like 2 weeks ago. So kind of a crazy thing. I guess parts of my chapters are going to need to be rewritten. No, not today. No, and it's rare enough. I don't think you guys care. So, but, so these are some different effects of the additional charge on these energy diagrams, and you can see as overall it typically raises the energy a bit. Anybody have any questions so far about that? Okay, so we've learned a lot about acidity and basicity and which directions are going to go, right? And so we learned how to explain the charged species and comparable uncharged molecules, relative acidity of species bearing the same charge, all the factors that are going to be the acidity of the proton, for example, the identity of the atom, the hybridization of the atom, nearby pi bonds, nearby atoms, are all going to be important to determine the acidity of that H+. And so how are these things going to determine those? What would you expect the acidity to do as you add something more electronegative to it? What does electronegativity mean?
An atom's ability to attract electrons.
Exactly. How well it holds onto electrons, right? So something with more electronegativity is going to be able to hold that negative charge better, isn't it? Yeah, it's going to make things more acidic. Okay? When you do these problems and think these things out, by the way, one of the things you should always do is if you get stuck, step backwards and use examples you've seen in your life. Okay? For example, you guys have the strong acids probably memorized, right? Do you have the strong acids memorized? Is perchlorate a strong acid? Yeah. Why is it a strong acid? Because it has lots of oxygens, yeah. So it has lots of the oxygens bound to that chlorine, and that makes it very, very acidic, doesn't it? Carboxylic acid is more acidic than an alcohol, isn't it? Okay? And you can use that to regenerate these same proofs, okay? All the things I tell you, you can regenerate from those. Okay, so let's go ahead and rate some different pKa's. Notice CH4 has a pKa of 48. We put nitrogen there, and what happens to the pKa? Goes down, and that means it's more acidic. Yeah, it's more acidic. And so we put an oxygen in place of that, and the pKa goes down even more, and that means it's more acidic, isn't it? We put a fluorine there, and what happens? Yeah, it becomes more acidic. Interestingly enough, the fluorine is still a weak acid. Yeah, hydrogen fluoride, very, very reactive, but not actually a strong acid. Still a weak acid. Okay, so the farther to the right an atom appears in the periodic table, the more acidic the protons attached to it are. And again, you guys generated this without me having to tell it to you. That's because it's more electronegative, right? So it's going to hold those electrons better. Okay? It's less likely to lose those electrons. It's more stable, holding on to a negative charge. All right. And again, that's the stability of its anion that we're looking at, isn't it? Again, the strength of an acid is actually how stable its anion is, how stable it is with a negative charge. Okay, and so let's go ahead and compare several different on-charged acids. Which one here would be a better acid? The one with the nitrogen, right? How about between the nitrogen and the oxygen? Oxygen's a better acid, isn't it? Yeah. And so which side would you favor? Yeah, the reactants. We're not going to have much going to products, are we? Okay. Okay, so let's go ahead and look at some charged species. What does putting a charge on these things do for us? Yeah, we're going to be, we're going to push up the energy of those reactants, aren't we? And so that's going to change our balance a little, okay? And so what we see here is that putting that H plus on here push these reactants energies up. Notice here we're going to greatly favor that side. It's the lower energy side, aren't we? But how about the H3O plus versus the H3O plus? Is that going to have any difference in between those two sides? No, they're equal in energy, aren't they? Yeah. So you're going to have no difference. You don't favor any side. Okay. Okay, so atoms in the same row, as we predict them in the periodic table, increasing the electronegativity of the atom is going to increase the atom bearing a positive charge, increasing the stability of the cation. And so the ability of the cation decreases as the electronegativity of the atom bearing the positive charge increases. Another way of saying that is, again, it's something that would have taken electrons very easily, and so it gaining in it a positive charge is going to mean it takes electrons even better, right? Yeah. Okay. So how about when we go down the periodic table? So we were following the electronegativity, weren't we? But when we go down the periodic table, HF was not a strong acid. HCl is a strong acid, isn't it? So we're no longer going to follow the electronegativity pattern, are we? Okay. What are we going to follow in that case? Well, we're going to follow charge density. Okay. So as we go down a periodic table, what you're going to see is the chlorine is going to be much larger, right, than the fluoride. Okay. And as we go down further, we get larger and larger, don't we? Okay. Well, remember, these are only going to have one extra electron. And so if you spread out that charge density, it becomes more stable, doesn't it? Okay. And so we can see that from the pKa's right there. So HF, 3.2, weak acid. Here we have HCl, it has a pK of -7. You've probably never seen that before. Most books just put it as infinite or strong acid. But remember, we actually have to keep track of these now. Okay. And so significantly stronger acid than HF, isn't it? And again, that's because of the charge density. As you go down, you can spread that negative charge across the anion better and better and better. Okay? This is going to be a true pattern in many different cases. Anybody have any questions about that so far? Okay. Okay, so this right here is going to be hybridization. So as we're going across and getting more double, triple bonds, what happens to that hybridization? Anybody remember? So for this, it's sp3, right? And it has very little s character. Okay? For this one right here, that's sp2, isn't it? It has a lot more s character. Okay? And the triple bond has an even more s character, doesn't it? Because that's just sp. Everybody remember that okay? Okay. So as we gain more and more s character, what we're going to see is it's actually easier and easier to share that electron density. Okay? And so it's going to absorb the electron density within its structure much easier and be much more stable doing so. Another way of thinking about this is that charged species, again, is going to increase the effective electronegativity of your atom that bears the negative charge here. Okay? You're essentially sharing more and more of that electronegativity of the other carbon. Does that make a bit sense? Okay. Okay. Okay, and so essentially as we go along to the triple bond, we get higher effective electronegativity, more stable negative charge. They become more acidic. Okay? And so this can actually be a pretty decent acid in organic chemistry, in case you're wondering. Yeah. This is not considered a very good acid. It's, in fact, a very poor acid in organic chemistry. It's kind of what we consider no real acidity. Okay? You can do it, but it's pretty hard, at least compared to triple bond. So right here we see the ethanoic versus ethanol. And again, these are both uncharged acids. But you'll notice that ethanoic acid has acid behind it. Ethanol does not. Ethanoic acid is a much better acid than ethanol. Okay? Why is that? More oxygen, exactly. Yeah, we have an extra oxygen there, right? And so more electronegative species. So not only can you get more electronegative and makes a better acid, but you can add more of those electronegative species, pull more electron density away, and get to be a better acid. Okay? This actually has even more effects, which is the resonant effect as well. And so in this case specifically, anybody remember how we drew those out before? So we drew it that way, but was there another way we could draw that? There was a resonant structure, wasn't there? Yeah, so you can draw this with the double bond down here and up there, right? Now what happens when we have multiple resonance structures? That means that structure is more stable, isn't it? Yeah. So we're actually providing even greater stability here. And that's why you get a pretty large increase. When we're looking at the carboxylic acids, they're very famously acidic, right? Versus something like an ethanol or a ketone, okay? All right, so this is actually the resonance structure. Does everybody remember ethanoic acid versus ethanoate? No? Okay, so when you have the acid, you put ic acid behind it, right? When you have the deprotonated conjugate base, it's 8. You ate it. Okay? Acid ic. Anybody know what flavoring the acids are? No? Sour? Yeah. So like a warhead. Everybody knows warheads, right? Yeah. That actually has such strong acid concentrations that has the same acidity as like a HCl sample. Yeah. It's pretty famous because they don't recommend you eating more than one of them at any given time because it can burn holes into your tongue and cheek.
I can feel it happening when I do this.
Yeah, it's actually awful. Like, how the hell that's something they can sell to kids?
It makes a lot of sense.
Like, just nuts, right? But that's one of the acids in it is citric acid, which is carboxylic acid. In fact, most of them are carboxylic acids of various types. So they're pretty crazy stuff. Anyways, this right here is going to be the resonance structure that we were just talking about. This actually is the anion of an ethanol, which is an oxide ion. So, etho oxide. Okay, so this is actually what the resonance structures look like. If you were to look at them without it being drawn in a two-dimensional way so we can easily understand it on paper, right? And so what you would see is you would actually see a sharing of that electron density between the two oxygens. Is everybody okay with that? Okay. And remember, those resonance structures, you really need to add those up to get the complete structure, right? No single resonance structure describes that structure completely. Okay. All right. And so here we see some different examples. Right here we have the HSO4 minus anion. Does anybody know what this is when it has all its hydrogens on it? It's sulfuric acid. Sulfuric acid is a strong acid. It's one of the 7 strong acids, right? Okay. And so this is why sulfuric acid is so strong, is because it will share that negative charge among those 3 oxygens in several resonance structures. Okay? And that means that, look at the charge density. See how it only goes yellow here? There isn't even a red spot, is there? Yeah, so that charge is very distributed, and it's very stable. It doesn't need the proton to come back on, right? On the other hand, this one right here has red spots. If a proton tries to come back on, it's going to be able to, right? Yeah. Okay. So this is going to be that presence of nearby electron. Oh, I'm actually done with time. I guess let's go ahead and call that a day. Yeah. In case you're wondering, I have like a little tiny time deal up on the top of my screen. And if I'm not specifically looking for it. Okay. You all have a great day.
Dr. King? So for the end of bibliography, which I see on my calendar, I'm still